Hi, folks. It's Mr. Roy. If you are either away from class or just want a little extra brushing up on our free fall and acceleration due to gravity problems, this video is for you. There's also a problem at the end that we did in class that involved two different accelerating cars, and it was a really challenging problem. So I'm going to go through that one as well. If you were in class, you'll have had a chance to try this out already. So first of all, I'm just going to say you have a note on free fall. And what I'm going to ask you to do is make sure to read through these key points here. I'm not going to reiterate them. Make sure to read them. They will help you out. Second of all, when we're solving for free fall stuff, we do have a couple tips here that are going to help you, right? Our acceleration is always 9.8 meters per second squared down. We're usually going to choose up as our positive direction and down as our negative direction, but you don't have to. If everything is moving down, it might actually be easier to choose down as your positive direction. And I'll show you an example where we'll actually look at that. Now, acceleration due to gravity, we normally write acceleration with an A, but when it's acceleration due to gravity in problems, usually we will put a subscript G right here, or sometimes this is just written as a lowercase g. These are both things you'll see, and your textbook, I think, uses the lowercase g, and that's equal to 9.8 meters per second squared, and that's down, right? When we have an object that we say is dropped, its initial velocity is going to be 0. A dropped object will actually behave like if you have an object where you, like in our picture here, where you throw it up and it comes back down, the velocity is 0 at the top. That's also true of an object that's dropped at the top. And a dropped object and the second half of a thrown up and coming back down object, those behave identically. Objects that are dropped from moving objects, like if you drop an object that's in a moving plane, it'll start with the initial velocity of the moving plane. That's something we don't do much in grade 11 physics, but you'd see more complicated problems in grade 12 physics. If you're throwing an object straight up, there is a moment at the very peak where it's essentially like the directions are changing, it's turning around, and we say at that peak that its velocity is 0. So if you're just doing a problem where you're throwing an object up and you're going to figure out stuff about the top, you can say your final velocity is 0 because that velocity at the top would be 0. If you're dealing with a problem where it's going up and down and you're trying to deal with it all at once instead of splitting the problems into pieces, then you wouldn't be able to do that. Be really careful with final velocity. If you have a dropped object, like here's a cliff and I drop a rock off of it and it goes like that. A lot of students will want to say, well, the rock hits the ground and stops, so our final velocity must be 0. And that's not true. When we're using our kinematics equations, we are looking for the motion in the falling part of the motion. So our final velocity would be the velocity right before it hits the ground, the instant before it hits the ground. The motion of it hitting the ground, it's no longer accelerating downwards at 9.8 meters per second squared. The ground is pushing up on it, and so it's actually accelerating upwards. So that's a completely different bit of motion, and we need to start our calculations all over again with new information. So final velocity is not 0 if it's an object that's falling and hitting the ground. Final velocity tells us the velocity right before it hits the ground. We're only dealing with motion as it's moving in Earth's gravitational field, not when it's hit the ground. That's a completely different set of calculations. Careful with that. That's a really common issue that students have. If objects are thrown up and come back down, a couple of important things. And I'll get out my highlighter for this. First of all, if they are thrown and land in your hand, they started and ended in the same place. So our displacement is 0. Okay? Our displacement is 0. You'll say, but it moved. It went up and back down. Yes. So it did have a distance that it traveled through, but its displacement is its change in position. Started in your hand, it ended in your hand, its displacement is 0. The time going up and the time going down are going to be equal to one another. They're symmetric, which is kind of cool. In fact, a ball that goes up and down, if you turn times backwards, you'll still get the exact same motion. So the upwards journey and the downwards journey take the same amount of time. That if they're landing at the same height. That means that we could actually only do the physics for half of the problem, from the hand up into the air, and then we could double the time. And we would know the time up and the time down because they're the same. The initial and final velocities, anywhere on our journey, the velocities on the upwards and downwards journeys are going to have the same magnitude but opposite direction. So you can see in the picture here, there's this green arrow, the upwards arrow and downwards arrow. Anywhere on the upwards and downwards journey where we're at the same height, the velocity is going to be same magnitude, opposite direction. So basically equal to one another, but pointed the opposite way. Okay. So that means the speed we throw it up with from our hand, if we catch it in our hand, it's landing in our hand at the same speed that we threw it up at. Last one, for an object that finishes above its starting point, if we've chosen up as our positive direction, then our change in displacement, or our displacement is up. If it ends up below our starting point, our displacement is down. Okay? So I throw a rock and it goes up in the air and then falls down off the cliff I was standing on the edge of, way down below into the ocean. Well, my displacement, it started on the cliff, it ended up way below in the ocean. I'm going to have a negative displacement. Okay, so be kind of careful with that. Okay, I want to share with you just a little bit about projectile motion. Here we've got our projectile motion cannon. I can shoot a cannonball like that. I'm going to turn air resistance off. And I'm actually going to point it straight up and down so we can have it do that kind of action. I can fire a cannonball, it'll go up, and then it'll come back down just like that. Now I can turn some vectors on here. In fact, I can turn my velocity vectors on. And we're going to see when I fire that, my velocity vectors change pretty dramatically. I have a really big velocity at the beginning, and I'm going to slow it down here, and I fire it. It's a big velocity. As gravity affects it, it slows down until it stops right there. Zero velocity right there at the top. Now, as it starts going again, gravity pulls on it, and the velocity increases. And so we get a bigger velocity vector as it goes down, just like that. Okay, so our velocity vector is changing, and it's zero at the top. Velocity vectors in opposite directions on the way up as to the way down. Now, what if instead I decide that I'm going to do acceleration vectors? Take a moment and just think about what you expect this to look like in the journey. Okay, this might surprise you. If we actually shoot our cannonball here, check out our acceleration vector. Our acceleration vector doesn't change. It's the same the entire time. The acceleration due to gravity. Acceleration just tells us how the velocity is changing. So as you're going up, your velocity is decreasing, meaning it's changing in the downwards direction. On the way down, your velocity is increasing in the downwards direction. So again, we have downwards acceleration. And even at the top, we still have that downwards acceleration. In that moment where the velocity is zero, the velocity is still changing overall more in the downwards direction. It's being accelerated downwards. So that acceleration is going to be constant the whole time. It's always negative 9.8 meters per second squared down. So that's kind of a really important point. Okay, let's go back to our lesson here. And we're going to solve some problems here. We're going to whip through a few example problems. So let's roll. Here we go. I'm going to go kind of quick here. You can come see me if you need a hand with any of this stuff later, okay? Make sure you're getting the support and help that you need with any of these problems. So again, if I'm going a little quick, come see me later and I'll give you a hand. First, we got to choose our directions, right? That's always what we do. Football's kicked straight up with an initial velocity of 15 meters per second. What's its velocity 2 seconds later? Let's choose our directions. I'm going to choose up as positive, and I'm going to choose down as negative for this. Let's write down the stuff I know. I know my initial velocity is 15 meters per second. I wrote it as a positive number because it's up. I know my time is 2 seconds. I won't bother writing the decimal place for that. I have my acceleration due to gravity, so that's not listed, but I know it's moving in Earth's gravitational field, so my acceleration due to gravity is going to be negative 9.8 meters per second squared. I chose a negative because it's accelerating downwards, always downwards towards the Earth. Now, you might have wanted to use G for that. That's fine if you use G instead of AG, no problem. Final velocity, I don't know, but I want to know it because it says what's my velocity 2 seconds later. There's one that's missing here, displacement, I don't know or need to know, so I'm just going to cross it out. That's going to tell me which equation to use. There is one equation that doesn't have displacement in it, and it looks like this. It's equation number 2. It's get my vector hats on there just to be proper. Okay, let's plug in my values. My final velocity is going to be equal to, my initial velocity was positive 15. My acceleration is negative 9.8. And my time is 2 seconds. Let's keep going. That's going to be 15. Negative times a positive is a negative, so minus 19.6. Let's add those two velocities together. I'm going to end up with negative 4.6. Now, I say, okay, what's it in? Well, my units were all in meters and seconds. This is a velocity, so this is going to be meters per second. I got to round it off to 2 sig figs. Looks like it's already at 2, so that's good. I don't have to worry about rounding anything off, but I would round it off to 2 sig figs. And so I'm now going to reinterpret my directions. Negative means down. So I'm going to write this as 4.6 meters per second. And then in the brackets, I can either write the word down or I could also use arrows like that. I kind of like those. That's a perfectly fine way to do it. I'll know what you mean. No worries. Okay, there we go. There's my first problem solved. Let's move on to example number 2. Okay, for example number 2, it says a high diver steps off a 27-meter high bridge. How long does it take for him to reach the water? Now, here's a little trick I'm going to try. Since everything in here is down, my displacement is down, right? You might want to write that as a positive displacement, but my displacement is down. My acceleration is down. My final velocity is going to be down. All my stuff is going to be either 0 or down. So I'm actually going to change how I write my directions. You don't have to do this. You could choose up as positive and down as negative like we did before. Your answer would work out fine. But I'm actually going to choose down as positive and up as negative just to show you that that's something you can do. Let's list our values here. We say, okay, our displacement is going to be 27 meters down. Down is a positive, so I'll write 27 meters with a positive. If you chose down as negative, you would write that as negative 27 meters because it ends up 27 meters below where he started, right? We always say to ourselves, displacement is your change in position. How has our position changed over the course of this motion? It's gone down 27 meters. You'll be tempted to use a positive. You'll be tempted to write that as a positive. So I chose down as a positive, and that makes that nice and easy. If you chose down as negative, it would be a negative. Our initial velocity, because he's just stepping off the edge here, is going to be 0. Our acceleration due to gravity is negative 9.8. Often students will be like, it's positive 9.8 because I chose down as positive. Meters per second squared. My time, I don't know. What's the one that's missing? Final velocity is not involved. I don't know it. I don't need it. So that's going to tell me which formula to choose. It's going to be formula number 3. Looks like this. There we go. There's my formula number 3. Let's plug some stuff in. Displacement is 27. Now, since my initial velocity and my initial velocity is 0, that means when I multiply my initial velocity of 0 times my time, this whole term is going to end up being 0. So I'm just going to write that like that. I put a line through it and a 0. That way I don't have to sub in a 0 and deal with all of that extra messiness. Nice, clean way to do it. So that's going to be 1/2. My acceleration is 9.8, and my time is t squared. So that means 27. 1/2 times 9.8 is 4.9 times t squared. 27 divided by 4.9. I'm going to divide both sides by 4.9. You can see how if I had negatives everywhere, my math would still work out, but this would be more annoying to deal with. So I end up saying, okay, time squared is equal to 5.51020. Now I got to take the square root of both sides because I don't want time squared, I want time. So time is going to be equal to the square root of 5.5102. That ends up being 2.3 seconds. Now you could, then I've rounded it to 2 decimal places for significant digits. Interestingly enough, the acceleration due to gravity, 9.8 meters per second squared, that is a measured value, right? It varies a little bit depending on where you are on Earth and how far you're away from the Earth's surface and like the density of the ground under you. It will vary a tiny bit. So that is a measured value. So we need to take that into account. So that's also 2 significant digits. I, though, would like to write the t on the left side when I'm writing my final answer. And it's seconds, and it's rounded up to 2 sig figs. So I'm good to go. Okay, that one we were choosing our directions the opposite way, and we were having to take the square root. Let's try it, number 3 here. A child throws a stone from the edge of a 20-meter high building with an initial velocity of 12 meters per second up. So they're throwing it straight up. What's its maximum height? And calculate its velocity as it reaches the ground, which would not be 0, right? It would be the velocity just the instant before it strikes the ground. Let's pick our directions. I'm going to call up positive and down negative. Let's write down the knows and need to knows. So we say, okay, initial velocity is going to be 12 meters per second. It's up, so I'll write it as a positive. My acceleration due to gravity is negative 9.8 meters per second squared. My final velocity is going to be at the top. At the very top, at my maximum height, my final velocity is 0. That's the moment where it stops, right at the peak there. My displacement, that's what I need to know. I'm not sure what it is. I'll put a question mark there. You'll notice time. I don't know it. I don't need to know it. So that's going to tell us which equation to choose. We're going to choose an equation that doesn't involve time. That's going to be equation 5. Final velocity squared plus initial velocity squared plus 2 times acceleration times displacement. You may notice that I didn't put vector hats on the squared values. And if you take calculus and vectors in grade 12, you'll learn why. It's because when you multiply a vector times a vector, weird stuff can happen. If you want to know more, I'll tell you more. Oh, sorry, that's not a plus, that's an equals right there. There we go, that's better. Okay, final velocity is 0, initial velocity is 12, and I got to square that. 2 times my acceleration due to gravity is negative 9.8. My displacement is the one I want to know, so that's still in there. Let's clean this up a little bit. 12 squared is 144. I'm subtracting 19.6, which is 2 times 9.8, times the displacement. Let's move the 19.6 times delta D over to the other side. Let's subtract it from both sides, or add it to both sides to get rid of it on the right and move it over to the left. So on the left now we have positive 19.6 times displacement. On the right side we still have the 144. Let's divide both sides by 19.6. Divide both sides by 19.6. I have just displacement on the left side. On the right side I have 7.34694. Sorry, that's getting a little messy. Now, you could just leave it at this, but its maximum height, it's actually thrown from the edge of a 20-meter high building. So its maximum height, if I want to know the height off the ground, I need to add that 20 meters to my number, because this 7.3 meters is only the height above the building, not above the ground. So I'm going to add 20 to this. So I'm going to write myself a little note here. I'm going to say add plus 20 meters for the building. Okay, so that means my actual displacement of the ball is going to be 27.34694. And if I round that off for significant digits to finish off my answer here, I do actually need to round it, so I'll put the squiggle. 1 sig fig, because that height of the building was 20 meters, that was 1, so it's just going to round off to 30, because it's closer to 30 than 20 meters. Displacement is a vector, so I need to say up. That's its maximum height. Okay, let's do the other part now. Calculate the stone's velocity as it reaches the ground. Here we go. Let's rewrite our stuff here. Initial velocity is 12 meters per second. Acceleration due to gravity is negative 9.8 meters per second squared. You can see how easy it is to miss a sign and then everything gets mucked up. Hey, so be careful about that. Our displacement. Now, you might say to yourself, displacement, let's see. Its maximum height was 27.34694. So that's what I'm going to put in for displacement. No, you got to be really careful here. Its displacement is literally saying what's its change in position from the beginning to the end. It starts at the top of the building, and then it's thrown upwards, and then it comes back down and it lands on the ground. So overall, from start to finish, where did it go? It started on the 20-meter high building, ended up on the ground, negative 20 meters. In the whole journey, it ends up 20 meters below where it started. Okay, really careful there. Now we say final velocity. We don't know, but that's what we want to find out. And I notice time is not involved here. So again, I'm going for that equation 5. Final velocity squared is initial velocity squared plus 2 times acceleration times displacement. Final velocity, we don't know, so we're going to leave it in there like that. Initial velocity is 12 squared. 2 times negative 9.8. My displacement's negative 20. Can I squeeze it in? Sure. Just barely on the edge there. Okay, I'm going to do some math here. I'm going to square 12. That's 144. I'm going to go 2 times negative 9.8 times negative 20. The negatives are going to cancel. It ends up being a positive. I'm going to add those two numbers together. I'm going to end up with a final velocity squared is equal to 536. Now, I got to take the square root of both sides, right? So final velocity is equal to the square root of 536. So that means my final velocity is, that's going to be 23. Okay, now you might say, good, I did it. But hold on, here's a problem. My final velocity is positive. I chose positive to mean up. That's a problem because my final velocity should be downwards. I throw the rock, it goes up. Well, Kate throws the rock. It goes up and then it comes back down. And right before it hits the ground, it's going down. Why did it get a positive velocity? Well, whenever we take the square root, our calculator is going to give us the positive answer. But we remember that we could actually have a positive or a negative, right? For example, 2 squared is 4, but negative 2 squared is also 4. So we don't actually know if it's a positive or a negative. We got to use our brains. Your brain needs to be smarter than your calculator. Your brain needs to be smarter than your calculator. Your calculator only shows you the positive number. You need to decide, is it positive or negative? In this case, we know it's negative. So our final velocity is going to be equal to, round to 1 sig fig, it's going to be 20 meters per second, and we know it has to be negative. It's got to be down. Okay, we know it's got to be a negative 1. And if you were doing a test or something, you would probably also want to put a note in here, and you'd say, choose negative because down. Right? Okay, so those are like our core problems. Now let's get into something that is a little bit trickier. Here we go. A rock is thrown upwards from the edge of a cliff at 25 meters per second. If the cliff is 60 meters high, how long does it take for the rock to reach the bottom? Okay, I should have put in like a Dwayne The Rock Johnson meme here or something. That would have been funny. Okay, so what I want you to do here is consider that this is a pretty complicated problem, but let's just start the way we normally do and see where we end up. Let's choose our directions. No, I don't want red. I want purple. There we go. I'm going to choose up as being positive, and I'm going to choose down as being negative. Okay. I'm going to write down the stuff I know I need to. Actually, let's do a little sketch, a little picture here first. Here's my cliff. Here's my rock that goes up, and then it comes back down to there. And we know that the height of the cliff is 60 meters from there to there. Okay. We want to know time, how long that journey takes. Let's write down our knows and need to knows. Our displacement is going to be, if you said negative 60, you're correct. Our acceleration due to gravity is going to be negative 9.8 meters per second squared. Our initial velocity is in the positive direction, 25 meters per second. Our time, I want to know. I'm not sure what it is. We're going to have to figure that out. Final velocity. Don't have it, don't need it. Let's get rid of it. Let's pick an equation. We're going to pick equation 3. Let's sub some stuff in. Negative 60. Initial velocity is 25 times t. Acceleration is negative 9.8 times t squared. So if we clean this up a little bit, we find something a little weird. You say, what do I do now? How do I solve for t? Well, what if I put an x where the t is? If I put an x where the t is, and I rewrote it like this, so I said 0 equals negative 4.9 t squared plus 25 t plus 60, because I moved over to the other side, so the sign changes. If I wrote it like that, and I said, what if the t's were x's? I bet this would look familiar to you. I bet you would say, aha, I know how to solve that. There's this thing called the quadratic equation that can help me solve that. We call this A, we call this B, and we call this C, and then we'd use the quadratic equation to solve for a quadratic. And I'd say, yeah, you're right. We can use the quadratic equation. So this is the first way to do this question. Students who like using the quadratic equation in math class will probably prefer to do this kind of problem this way. I don't, but you might, and that's great if you do. So we'd say, okay, quadratic equation, I'll use a t instead of an x, is negative b plus or minus the square root of b squared minus 4ac over 2a. Let's plug in some of our values. I'm going to do this kind of quick, so just be aware that I'm not going to go through every little tiny step here. If you want to know each of them, you can come talk to me about it. Negative b would be negative 25 plus or minus b squared is 25 squared minus 4 times negative 4.9 times negative 60. Okay. And, oh no, sorry, positive 60. Our c was positive 60. There we go. So I can see there's a whole bunch of stuff in the under that square root that I'm going to have to work out. 2 times negative 4.9. If I clean this up a whole bunch, here's what it ends up looking like. I end up with my negative 25 plus or minus square root of 1,801. And 2 times negative 4.9 is negative 9.8. So that's what I got to do. Plus or minus is looking pretty rough. So I go negative 25 plus the root of 1801, and then divide all of that by negative 9.8. And then I do the same thing. I go negative 25 minus the square root of 1,801 divided by 9.8. I'm going to get 2 answers from this. So my 2 answers are, the first one is 6.88 seconds, or my second one is negative 1.78 seconds. Now, I've got a negative value for time, so I'm not going to include that. We're not going to be doing any time traveling in this question. So that means that my positive value is the one I want to choose. So if I round that off for sig figs, that's going to round off to 7 seconds. Okay, so that is one way to do it. We said we set up our problem, we plugged it into our formula, we found that we had a quadratic. This can happen with the formulas 3 and 4. Anytime we're solving for time and the initial velocity isn't 0, this would happen. We'd say, okay, put it in standard form where we got a 0 on one side, everything else on the other side, use quadratic equation, chunk it through, look at our 2 answers. Usually one will be positive, one will be negative. Well, in every case like this, it'll be positive and negative. Get rid of the negative one, take the positive one. Bob's your uncle. We figured out the time to reach the bottom. It's much easier when the initial velocity is 0. We don't have to do the quadratic equation. But in this case, we did. Now I'm going to teach you another way to do this that doesn't involve using the quadratic equation. So you might like that a lot more. Me personally, that's how I like doing it. I'm not a huge fan of the quadratic equation. So what I'm going to do is I'm going to make a new page here. And I'm going to put the basic stuff right here that we started with. But instead of getting rid of final velocity and saying we're not going to use it, I'm just going to do this. I'm going to say final velocity is also one we don't know, but we would like to know. The velocity right before it hits the ground on the bottom of the cliff there. Now we got 3 knowns and 2 unknowns. We could solve for those 2 unknowns. We already did solve for t. Let's just try solving for final velocity. Here we go. I say, okay, the question didn't ask for this, but I'm going to solve for final velocity. Final velocity squared equals initial velocity squared. Oh, sorry, I shouldn't have the vector hats on those. Let me get rid of that to be proper. Final velocity squared equals initial velocity squared plus 2 times acceleration times displacement, right? Plug our stuff in. Final velocity squared is 25 squared plus 2 times negative 9.8 times negative 60. Now, if I work all that out, I get 1,801. And then I got to take the square root of that. And does that look familiar? It should. We ran into it right here when we were solving for time. We had negative 25 plus or minus that value divided by 9.8. Okay? So we're going to find that this math is going to actually work out identically. Doing the problem this way, we are doing 2 calculations instead of 1. We're doing 2 calculations instead of 1. Now, why is it turning red? Guess that's fine. Final velocity. Now, it's going to be plus or minus, right? Because we're taking the square root. 42.43819. It's plus or minus. We're going to choose negative because it's down. We know the negative has got to be the one we want as a solution for that. And if you want to get into like the intricacies of why there's 2 solutions for it, I'm happy to chat with you about that. It's kind of interesting. But for this purposes of this tutorial, I'm going to skip ahead. That's our first calculation. That's step 1, right? So we'll say, okay, that's going to be step 1. Find final velocity. Now let's do step 2. Step 2, find time. Okay. Now, I want to find time. That's going to be kind of easy because I can use this nice, easy equation. That's equation number 2. Final velocity is negative 42.43819. Again, we realize why vector signs are so important. Equals 25 plus acceleration is negative 9.8 times time. Now, this is probably looking familiar to the thing on the last page. It's in fact the same equation. If we rearrange this, right, we subtract 25 from both sides. We're going to say, okay, we end up with negative 25 minus 42.43819 equals negative 9.8 times t. Divide both sides by 9.8, and you actually get this value, this thing. Get my highlighter out. You get this thing right here. So we're just calculating it 2 different ways. Okay. So we'll divide both sides by negative 9.8. So we say negative 25 minus 42. That ends up being negative 67.43819. And I divide both sides by negative 9.8. So we end up with negative 9.8 over here. That's all going to equal t. I work that out, and I get t is equal to 6.8 8. Round for sig figs, it's going to be 6. It's going to be 7 seconds. It's the same answer. So I want you to think right now. What do you want to do? What do you want to do, hotshot? What do you want to do? Do you want to use quadratic equation? I find each year about a third of the students like to use quadratic equation for this problem. Or do you want to solve for the fifth unknown, the fifth variable, and then go back and do another calculation to solve for the fourth? Do 2 quick calculations. Which do you like better? Me, I like doing the 2 quick calculations better than using quadratic equation. Some people really like quadratic equation. Up to you. Give it some thought. What do you prefer? But that's how we would solve that problem. Let's do one final problem. It's a doozy. This is from the Check Your Understanding sheet, and we did this one in class. Started working our way through this. It is a bit tricky. So I'm going to walk you through this. Now, Mr. Clark is going to cover this in class on Wednesday. So if you're going to be in class on Wednesday, you can ignore this and maybe skip this part, and you'll get to see it at the beginning of class tomorrow. But if you are going to be away on Wednesday morning, this is for you. Okay, here we go. We got a car and a police cruiser. The car is moving at 35 meters per second. That's constant speed. It's not accelerating. Constant velocity. At the instant the speeder passes the cruiser, the police officer hits the gas and accelerates. So, car, not accelerating, uniform motion, constant velocity, acceleration equals 0. Police cruiser, accelerated motion. They are uniformly accelerating. So the formulas we're going to use are going to differ for these 2 situations. Okay. Here's the key idea here. How long does it take for her to catch the speeder? We got to say to ourselves, what are we really looking for, right? We know there's some time, that's how long, there's some time where their displacements are the same. So we're actually going to set their displacements equal to one another and then solve for time. How did I figure this out? Because I'm a physics teacher, that's how. But this is my thinking process. I know I need to find time, and at some time their displacements will be equal. So if I can set up a formula for the motion of each of them, and then set the 2 displacements equal to one another, then I can solve for time. Let's go for it. Here's our car. For the car, I'm going to use the subscript C. The speed of the car, I should pick directions. We're going to say forward. For both of them is the same. Forward and back. Forward we'll call positive, back we'll call negative. Speed of the car is a constant 35 meters per second. Positive because it's going forward. Displacement, we don't know. I don't need to write the displacement of the car because we know their displacement will be equal at the point we're interested in. Time when they meet, I don't know. Let's write our equation. Velocity of the car equals displacement over time. Let's rearrange this equation by moving the time up here. So we end up with speed of the car times time equals the displacement. Okay, now let's sub in for the speed of the car. It's 35. So 35t equals the displacement of the car. Now let's do the cruiser. You may notice cruiser starts with the letter C, so I'm going to use P for police. Okay, we say what's the initial velocity of the police cruiser? It's 0, starting from nothing. What's the acceleration? It's the only one that's accelerating, so I'm not going to give it a subscript because I know there's only one of them that's accelerating. It's 5 meters per second squared. What's the final velocity? Police final velocity. Don't know, not sure. What's the displacement? Not sure, but it's going to be the same as the car at the point we're interested in. What's the time? Don't know. So we don't have enough information there. We need a third one in order to solve for a fourth one. But let's set up our equation. I'm going to set up an equation that involves time, displacement, and then the stuff I know, initial velocity and acceleration. So displacement of the cruiser is going to be initial velocity times time plus 1/2 acceleration times time squared. That's equation number 3. Let's sub in some values. Know my initial velocity is 0, so I can get rid of this whole term. It's gone. That simplifies things. Then I have a 1/2 times 5, that's my acceleration, times time squared. Simplify a little bit further. 1/2 times 5 is 2.5 times t squared. Now, okay, we have our equations for the motion of each vehicle. Let's compare the two. I'm going to set the two displacements equal to one another because I know when they meet, that's what's going on. When is their displacement the same? I'm going to set the two displacements equal to one another. And when I do that, see what I get for time. For my car, I said the displacement was 35 times t. That was my equation. For my police cruiser, I said my displacement was 2.5 times t squared. Okay, great. Let's divide both sides by t. So a t drops out of each side, and we're left with 35 on one side and 2.5 times t on the other side. Now let's divide both sides by 2.5. I do that, and I'm going to end up with t equals 14. Now, I got to check the sig figs here. 2 sig figs. So it's already at 2 sig figs, so I can just put seconds and put a box around it. They have the same displacement at 14 seconds. Now, that's kind of a nice, elegant way to solve it. You could solve it just by checking times until you manage to get ones that matched up. But by setting them equal to one another, I say I'm checking that point and seeing what the time is. It's a tricky problem, but a goodie. I hope this has helped. Talk to you soon. Come in and see me if you need a hand. Bye for now.